So, good afternoon, everyone. Thank you for the very kind introduction. And I'm from just across the river. I've been here for at least 10 years, but I've never been to IRNS until today. So it's a pleasure to be here. Though I've met a lot of people from IRNS through various interactions. Okay, so this talk is about how we can connect concepts from physics to chemistry, specifically electrochemistry. I don't know why that. So we have the chemist and the physicist. So one is Faraday and one is Daniel. So the two started very close, and they diverged. And I think now they're past 50 years, they're becoming closer and closer. And so we want to tackle these problems because there's lots of energy solutions that can be found through enhancing our understanding of these processes. And also there are new devices possibly that can be realized, such as in cognitive computing and in some manufacturing processes. Actually, the integrated circuits are electrochemically deposited for copper interconnects in your chips. Okay, so let's move on to the nexus of the talk, which is basically a kind of tutorial type results research talk mixed together. And what we're looking at is this interface between physics and chemistry. All right, so this is typically the domain of the chemist. This is typically the domain of the condensed matter physicist. Now, when we look at electrochemistry, we have to add in a little bit more here, for the most part, where we include what are called supporting electrolyte ions. These do not participate in the reaction for the biases considered, but they play a very important role, we'll see. And then for the reactions we're going to consider, there are two types. There's oxidized and reduced species. The oxidized species will take an electron, they can grab one, and the reduced species will give an electron up. And so in a very simplistic picture, what we have is a voltage drop that we apply between the solid and the liquid. And when we do that, we induce a potential drop right at this interface. And this is caused by having a very high supporting electrolyte concentration. The distance over which this potential drop occurs is a matter of some debate. But basically, the more supporting electrolyte ions you have, the shorter the distance, and the more you can facilitate the reactions that we're going to talk about. And then in the solid, we're going to talk about metals. You have a very, very short screening length, less than a nanometer, typically a bond length or two, over which the screening occurs. So that means that the voltage drop occurs at a very short distance, and most of the stuff that we're interested in goes on right at the interface. Okay, so what we're going to look at is the electron transfer process and how this occurs at these interfaces. All right, so the oxidized reactant that's shown here, this is something that will grab an electron from the solid, and the reduced reactant is something that will give up an electron. We'll look at that later. So the type of reactions we want to examine here are what are called outer sphere reactions. So there, at the end of the talk, I'll do a comeback to this slide, and we'll see that we'll discuss that there's a wide range of reactions, and the ones we're going to talk about here are specifically a small subset of very complex set of reactions that happen in electrochemistry. But these reactions provide a good place to start, these tunneling reactions, because you can describe them with the intuitive pictures that we're going to go through. So the two main goals that we're going to discuss in this talk are to explain two, in the language of physics, IV curves, current voltage curves. So we're going to talk about this type of curve here, and then we're going to talk about curves where you have a peak and then a drop and a peak and a drop. Okay, so we'll talk about just having one peak, and we'll also talk about having multiple peaks and where these come from the perspective of physics. Now, if you were to describe in language of physics, you'd call this an IV curve. If you were to describe this in a physics context, like to have an electrical device, you would use the electronic structure picture to understand where this IV curve came from. And so the argument of this talk is that you can similarly use electronic structure to understand current voltage, or what's called voltammetric features in electrochemistry. Okay. So in order to put the two concepts on the same ground, we need the same language. Okay? And that language in physics is based on what are called single particle energies, or electronic, if you like, you can call them electronic structure energies. So in the simplest manifestation, this is an energy to ionize or remove an electron from a solid, or the energy at which an electron can be put on a solid. So these are ionization affinity energies. Now, the important step that occurs when connecting the electronic structure picture to the chemistry picture is that these energies here, these electronic structure energies, come from differences in total energies. You're looking at the change in the total energy with respect to changing the number of electrons to go from example n to n-1, or vice versa, to put the electron back on here. Okay, so this gives rise to this picture shown here, which is a very simplified but decent phenomenological picture of what a metal looks like to most physicists when they're trying to understand conduction. And so this sort of picture goes on, and we treat concepts like the Fermi sphere and how this Fermi sphere shifts when you apply a bias to a metal, how conduction occurs. It all occurs in understanding where electrons go in solids using this electronic structure picture. So we have, in the case of a metal, a continuum of empty states above what's called the Fermi energy or electrochemical potential, and then filled states below it. And so when we understand current flow inside solids, we use this picture, this electronic structure picture, extensively. So if you go and you read a paper that's from the solid state physics or device physics or associated engineering communities, you will see pictures like this, except if it's a semiconductor, it will have a band gap. Or you'll see a metal junction and you'll see this picture. And this is used to explain the current voltage characteristics of electrical devices. What we're going to look at is how we can use this same technique to explain electrochemistry. Now, the important point here is that when a physicist is introduced to this picture, if you take a solid state physics course, you'll never consider the change in nuclear coordinates. You'll just see this picture, you'll touch upon it in an exam, and you won't go much further with it. And the reason you don't go much further with it, at least in terms of what's happening with nuclear coordinates or the positions of atoms in solid state physics, is that in metals, electrons are delocalized over billions times billions of atoms. So many, many, many atoms. So when you add or remove an electron, there's very little charge change on any given atom, say 1/1000th of an electron density. And so that impacts on very little on the nuclear coordinates, and therefore there's no change in the electronic structure when you add or remove electrons. In chemistry, the picture is completely different because electrons are localized. There is an analog in solid state physics where you do have change in electronic structure with change in nuclear coordinates. Polarons are the prime example of that. And we won't get into that in this talk, but there is a bridge of a continuum of ideas that bridges all of these together. That's the point. Okay, so we talked about the solid. What about the liquid? So in the liquid, we can go through the same idea where we pick a certain ion, let's say, for example, here, iron 2+. This is very cartoonish graphic picture, but we have a solvation shell, and the closest that we have is this coordination of 6 water molecules, and we pull an electron off. And if we're going to kick an electron off, for example, with a photon, there's a cost to doing that and bringing the electron up to vacuum. Okay, so this is what we call a reduction energy in the single particle or electronic structure picture. This is the energy to take an electron off a reference. The important point here is when we look at this change in energy, this total energy change that happens, and give it an electronic structure energy, it's at a specific nuclear coordinate that happens. We label this -1 here. It didn't have to be -1, but we just picked this notation. So Q is the nuclear coordinate. Once we remove that electron, the ion is in a different charge state. And so there's a nuclear coordinate change, what we call a reorganization in the chemistry literature, that brings these water molecules a little bit closer. It's actually a very small change, an angstrom or less change, but has a actually substantial impact on these energies. And so these water molecules come in a little bit closer because the charge state has changed. So we have a different preferred minimum of our nuclear positions. And so if we try to put the electron back on here now, it will be at a different nuclear coordinate. And so when we put the electron back on, it will be at a different electronic structure energy. This is called the oxidized single particle energy. And the reason we'll have a different energy from the chemist's perspective is that we're doing it at different coordinates. We're changing the number of electrons, but we're doing it, the 0 here is coordinate. We're doing it at different nuclear coordinates. Okay? If this, we'll see at the end of the talk, if this was a material that didn't undergo any reorganization, the energy to add or remove an electron would be the same if the coordinates don't move. But you allow the coordinates to move, you'll have different energies at which you add and remove. Okay, so the key difference in using electronic structure in chemistry problems like this is that there's a change in nuclear coordinates, and that makes sense because kinetics, which is the motion of nuclear coordinates, are facilitated by the motion of nuclear coordinates, is a lot of chemistry in addition to thermodynamics. Okay, so what we have here is a picture of the liquid where we add or remove electrons at specific electronic structure energies, unoxidized and reduced energy. And so we drew this picture here. This is the energy to remove. This is the energy then I put the electron back on. Then we have a picture of the metal where we can add or remove electrons. This is this band structure picture, band diagram, or density of states picture. They're all more or less the same thing that we use in a metal, and we use vacuum as a reference in the electronic structure picture rather than a reference electrode if you're an electrochemist. Okay, so the question is, how can we use this electronic structure picture to explain a current voltage curve like this, or what's called a voltammogram curve in electrochemistry? To do that, we need to go beyond just looking at adding and removing electrons from specific nuclear coordinates. We need to look at how it can be done at all possible nuclear coordinates. So this is the beginning of what's called the Grischer model or the Grischer-Hopfield model. And so what we have on the lower axis here is the range of nuclear coordinates that can be accessed. So the solvation shell is either expanding or contracting, depending on which direction you go along here. And then this is the total energy of the system. Okay? So if we just take the solvated ion and the electron as one system, there's a cost to remove that electron and put it up to vacuum. So if we were to take that electron from this system and move it up to vacuum, we'd go to the blue curve here, because now the whole system, the electron plus the solvated ion, are at a higher energy. The electron in this Fe3+ state is sitting somewhere far away, let's say a distance off from the solid, but we can bring it back on. We'll do that later. Sorry, distance off from the liquid. And so here we have again a parabolic minimum, but it's a different position because we have a different charge state, different preferred nuclear coordinate. If there was no change in nuclear coordinates, these two parabolas would be on top of one another. They'd be at the same coordinate. But here they're shifted because there's this reorganization that happens from adding and removing electrons. Now, what if we then put the electron back on this Fe3+ state? What happens is that the total energy changes from here to here. And it's this change in energy, which is what we call an electronic structure energy or a single particle energy in physics. It's change in total energy, this specific nuclear coordinate. And then after we put the electron on, the nuclei respond following the Frank-Condon principle. And there's a reorganization. And this difference from energy as the nuclei go from this preferred position to a little bit further out is a reorganization energy. If you know Marcus theory, this is very similar to Marcus theory, except for the fact this is half of the Marcus reorganization energy. There's a reason behind that, because you're only considering, in this case, one ion instead of two ions, but all these concepts can be mapped directly to Marcus theory. All right, so if we then do the reverse, we're back here, we put the electron on, we came down here, we kick it off, we end up back here again, and there's a change in the total energy, and that's this single particle energy, or electronic structure energy. Again, there's a reorganization to go, now that we've gone to a 3+ state again, to go to this, back to this minimum. So these two electronic structure energies for oxidized and reduced states are separated by twice the reorganization energy. And this is something this is common in many review papers that discuss this type of electrochemical phenomenon. Now, what Grischer and Hopfield did was expand these concepts to not just consider two particular coordinates at 0 or -1, as we've used this notation here, but what if we can add or remove electrons at any given nuclear coordinate? So this is I don't know why this little zoom bar is up here. Let's see if I can move that. Yeah, I'm trying to go away zoom. No matter where I put it, it's inconvenient. Maybe I'll try for that. Okay. But I think I'm recorded through this. Yeah, okay, all right. I'm not sure if I'm going through this microphone or through the computer, but okay. So if we look at these two pictures here, this is for the oxidized and this is for the reduced state. If we want to get a range of what's the electronic structure energy for adding and removing an electron at any given these nuclear coordinates, well, we just subtract the two. And using this harmonic, oh, now my, okay, well, that's not working. Now, if we remove these two subtract these two, we get this linear possible electronic structure, single particle energies for adding and removing electrons. Now, what Grischer and Hopfield did was they said, well, we're not going to add any of these energies. There's a reason why we chose to start with this oxidized and reduced energies. These are the preferred energies, where most of the time we'll add and remove electrons. And so what happens is there's a probability, most of the time will be at the minimum, but there's an exponential probability of going away, according to Boltzmann statistics, from this minimum. So if we consider the probabilities of being around these different nuclear coordinates, that corresponds to the probability of being at these given single particle energies. So this can give us a distribution, what's called a Grischer distribution or Grischer-Hopfield distribution of electronic structure energies for adding and removing electrons. So if we go back to our original goal, which is to take the solid and the liquid electronic structure and put them together, we can take these same energies here, these oxidized and reduced electronic structure energies, and plot them here and here. And then about them, we have a density of probable states that will be occupied. So this is called the oxidized states, and these are called the reduced states. These states only accept electrons. These ones only give up electrons. And they're separated by twice the reorganization energy. And now we have a basis to put the electronic structure of the liquid next to the electronic structure of the solid. And the reason that's important is now we can use electronic structure theory to understand these types of current voltage characteristics and where they come from, either this plateauing feature or the peaked feature that was shown in the introduction slides. And all of this is outlined in this paper published last year. Okay, in a review format similar to this talk. So what we want to do is put these two together, the water and the solid, the liquid and the solid, and we want to use the electronic structure picture to understand those types of IV curves that we just examined. And the first step to getting an IV curve is we have to get a rate. What's the rate of an electron going from the solid to the liquid? And if we multiply charge by rate, we'll get a current. So in order to get a rate, we have to do a little bit of work, but it involves using basically Bourdain's tunneling theory and Fermi's golden rule. And without deriving all of this, because it takes another 20 minutes, but we have a density of states in the solid here, we have a density of states of the oxide species, and we get a corresponding tunneling rate from the quantum mechanical coupling between the wave function in the liquid and the wave function in the solid. And the density of states, if you're not familiar with it, it just tells you the number of electrons that you have per electronic structure, or what's called in physics single particle energy. Okay, so the point is that we can get a reaction rate from all of these concepts, okay? And a reaction rate that matches experiments, as we'll see shortly. So there's a rate, what we call a forward rate, where we take electrons off the solid and we put it in the oxidized state, and a backwards rate where we remove electrons from here and it goes to an empty state in the solid. So there's a forward and backwards rate. Now, what we want to do is put all this together to understand an IV curve from electrochemistry. So this, again, are tunneling reactions that are happening here, and we're going to take an electron from here and put it on this ion here. Okay. And what we want to understand is the IV curve that will result. Notice this is absolute and on a log scale. So if we take the picture that we had here, ignoring for now that there may be subtleties like a interfacial absorption drop here, we'll just keep the vacuum, the 0 electron volts, the same for both the solid and the liquid. What we do then is we apply a bias across the system. There's electrons that build up here in this example, and then positive ion charges that build up on the other side, like a capacitive response. And what that does is it creates a voltage drop right at this interface here. Okay? And as you create a voltage drop at this interface, this capacitive junction right here, tunneling process can occur where the electrons go from the filled states to these empty oxidized states. Following this rate equation here, we multiply by charge and we get a current that's occurring. Now, the important point is that the distribution of states that you tunnel into exponentially depends on the electronic structure energy. So as you move this past further and further past this, you get an exponential increase in the availability of states, and that gives you an exponential rise in current. This is usually called a Tafel slope in electrochemistry. And then for this particular type of system, you get a plateauing in your electrochemical current, and that's because now all the available states are being tunneled into. There's no more further states to access. And so this is how you can take an electronic structure picture and explain electrochemistry. So the same type of framework that's used to explain, for example, how a diode works, a Schottky junction, a CMOS transistor, electronic structure used to explain electronic device, you can use to explain these types of electrochemical reactions. Okay? It's the same framework. The only difference is now you have to take into account the reorganization or the change in electronic structure with electron addition or removal, and the current plateaus around the reorganization energy. Okay, the same you can do in reverse. You reverse the polarity. You have positive charges or a deficit of electrons over here on the metal. You have negative ions building up the capacitive junction, and that induces a very sharp potential drop in the interface, which can then pull these states by this filled state here. And as you pull it by, the more and more can tunnel this exponential distribution, and you get an exponential rise in current with respect to bias. And then as you pull the entirety of your state within your bias window, you get a plateauing for this particular example. So the important point here is the take-home message. I know we went through all of this pretty quickly, but the take-home message is that you can use electronic structure picture to explain IV curves in electrochemistry, just as you can in the solid state. In the solid state, this is called a band diagram, and you would use a band diagram to understand how a diode works, how a transistor works. There are huge textbooks which explain exactly this technique. For solid state problems, you can use the same approach for electrochemical problems. Now, if you're wondering, are there experiments which show these IV curves? It's not just theory. There are some seminal experiments that show exactly this behavior. This is a tunneling experiment to a ferrocene group from CHIDSI. This is a very famous experiment in electrochemistry. And we also have some other experiments that show the same behavior, this well-known book, at least to the physical chemistry community, describes this. So I won't get into that in any depth, but what the point here in this slide is that the theory matches the experiment. Okay, this model works. This way of thinking, which started from Grischer, can really be used, this electronic structure picture. Okay, so for those of you that are not electrochemists in the audience, there's some subtlety when you look at an electrochemical current voltage curve, what's called a voltammogram. And that subtlety is that what you're doing is you're scanning the voltage in a time-dependent manner. So you're sweeping the voltage over a given amount of time, and you're measuring the current that results for that sweep time or that sweep rate. And so the sweep rate has a very dramatic impact on the current that you'll measure because you're transferring electrons to a concentration of species. In this case, we're forward biasing, so we're transferring to oxidized species. And so as you transfer electrons to oxidized species, the concentration, they'll convert to reduced species, will deplete. This will go down and down. So this concentration will change as you sweep the bias. So if you do it very quickly, say in a microsecond, you can get this type of curve here, where you don't give enough time for this concentration to drop down. But if you scan more slowly, as shown in this animation here, what happens is that this oxidation concentration reaches a peak and then it drops down. So there's sort of a competition between these two terms, and this term comes to dominate. And so you get this peaking effect where the concentration times the transfer rate maximizes, and as the concentration drops down, it falls down. And so one of the important points is that this peak can shift. Here we're talking about redox experiments. This peak can shift depending on the scan rate. So there's some subtlety in that. But this is the same model that we showed before, and you can explain the plateauing curves, you can explain peak curves, at least for tunneling reactions, using all of the electronic structure picture that we just looked at. So there's a wide range of reactions. For example, in a flow battery, you can explain the reactions of a flow battery using all of these pictures here. Okay, now I'm going to get, hopefully I'm not going too quickly, but I'm going to get a little more into the heavy physics. This is the less tutorial part of the talk, and show that we can do some really fancy physics in electrochemistry. All right, so one of the interesting things of physics, which is called Coulomb blockade, is where you can add many electrons. Or another example is Frank Condon blockade that we'll briefly touch upon on the end. And In electrochemistry, you can also add multiple electrons to a species. Buckyball is one of the first examples of that, or C60 or C70, back 30 years or so ago. And the argument we'll make here is that you can explain these types of IV curves or voltammetric curves using electronic structure descriptions, electronic structure theory or band diagram theory. And you can also gain new insights into what these peak separations mean from an electronic structure perspective. And this electronic structure we're talking about is the electronic structure Hamiltonian you would have learned in a quantum mechanics course. Okay, so if you unpack the Hamiltonian in a quantum mechanics course, you have what is called the quantization, or physicists call this a kinetic term. It's not the kinetics for a reaction barrier. They just ran out of words, or they use a different language. For the chemistry notation, I usually call this a quantization term. This acts on the wave function. Then you have an electron-electron interaction term, and you have an electron-nuclear term. And when you go to small systems, all of these terms are very important. Now, what's very interesting is that this term, the quantization, electron-electron interaction term, drive these peak separations that you can see in a multiple electron transfer voltammogram. So if we were to take the solid state system and think about frozen nuclei, if we had an energy level that was isolated here and we tried to add another electron to it, there would be a Coulomb cost of doing that, a U interaction between the electrons. So there would be a shift in the next energy level. This is called Coulomb blockade in physics. Now, if we don't have degeneracy in our energy levels, the next energy level up would have both a Coulomb cost to then add a further third electron, plus this quantization K cost. And then if we want to add a further electron to go to 4, we'd have the further quantization cost that we already encountered, and then a further U cost. So the point here is that these quantization, these U contributions all appear in this type of electrochemical spectra, and you can pull them out just as you can, for example, in Coulomb blockade in physics. What you have to do to map the physics to the electrochemistry is introduce what Hopfield called Stokes shift. Okay, so this is often called reionization in the chemistry literature. Hopfield, being a physicist, calls this Stokes shift, and it's very much related, or essentially identical, to Stokes shift that you see in optical spectroscopy. Okay, don't have time to get into that, but I'm happy to discuss it later. So what we have here is a process where we've changed the picture, we've split the levels into oxidized and reduced states, and as we sweep a voltage past each of these accessible electronic structure states, we'll see a peak. So that's our first, this is our first peak, and then we'll fill the next peak. That's our second peak shown up here, and then we'll fill our third peak, and then our fourth peak. So there's a way to map these peaks that are seen electrochemically to electronic structure that's occurring in solution. And what's very interesting is that independent of the scan rate, these peak separations are quite robust. So you have fairly stable estimates of what these values are, even in the quite statistically messy system that is often accompanying electrochemistry. Now, this was a lot of theory, and the question always becomes, where's the experiment? So this has been seen in many landmark experiments. Here we have, there's still newer experiments ongoing, but these are some of the landmark ones. Here we have gold nanoparticles, and as we shrink them, for example, from 137 to 43, we see these peaks. Okay, there's a little bit more to it that we're not discussing here in getting these peaks, but anyways, you see this separation here. This is kinetic and coulombic. Here we have very similar peak separations here. These are these U costs, these coulombic interactions between electrons in an electrochemical system. Then we have these Buckminster-Fullerene type reactions. It's a famous experiment from about 30 years ago, where they see multiple electron transfer peaks that are all similarly separated. Why are they all similarly separated? Well, we can explain this using the same model we had just shown here. And the reason they're all separated is that the buckyball, the LUMO level, in this case they're adding electrons, so it's to the LUMO level, is 6-fold degenerate. Okay, so the kinetic, there are very few quantization changes. You're just adding electrons, same degenerate level, and there's a U cost adding each electron, and you can add them 6-fold, in this case 5-fold, and the separation will be the Coulomb cost of adding the electron each time. And here we have experiment, and we have theory. There's a wonderful match between the two of them. just from taking this band diagram, this electronic structure picture, and applying it to electrochemistry. So if this was a solid state device, a metal and a semiconductor, we would use electronic structure theory to explain the IV curve. Here we're arguing that if it's a solid and a liquid, you can use this same electronic structure methodology to understand it. And the reason we want to use electronic structure is it tells us where the electrons are and where they're going to go next. That's the beauty of electronic structure. It tells you where the electrons are and where they want to go. So a recent application of this method that we just published in PRX Energy and last year in Journal of Physics Chem C was looking at how we can engineer these redox peaks for multiple redox reactions. And it turns out these nanodiscs make for a beautiful system because they have highly amphoretic properties where you can easily add or remove electrons from them and they remain stable within the electrolyte window. So in this analysis, this study we did, we looked at the ultimate limit of how closely you can put these redox peaks together. How would you go about doing that? By tuning the size, the U term, the quantization term, the electrolyte around it. And it turns out you can get a near ideal Faradaic response that looks like a capacitive response. This is called pseudocapacitance. So if you were to sweep a double layer capacitor, you'd see this type of response. But this type of response comes from these multiple Faradaic reactions occurring and overlapping so closely together from this quantization mechanism. So in this study that we did, where we combined electronic structure to look at a new avenue of exploration in electrochemistry, we speculated on whether one could construct, for example, a pseudocapacitive battery using these means, where you could use the highly amphoretic properties of nanodiscs and their two-dimensional character to pack volumetrically a lot of disks into a reasonable space and use fast electron transfer processes to achieve fast charge storage. And maybe this is a method where you could get an ideal pseudocapacitive response where it has the speed maybe of a supercapacitor and the energy density, at least volumetrically, of a moderate battery, for example, nickel metal hydride. Not lithium air, but something moderate. So this provides a new axis of exploration that comes from these ideas of connecting electrochemistry to electronic structure. Okay, so at the last part of the talk, I want to do a final overview application where we look at how we can look at fully quantum redox chemistry, how we can use a fully quantum description and see redox processes. So as we talked about at the beginning of the talk, if you have a large medioscopic particle, which is something that physicists might typically look at, we'd add or remove an electron. And because the particle has millions or billions of atoms in it, in, for example, Coulomb blockade, these total energy curves, their nuclear coordinate minimum, are right on top of one another. So the energy which we add or remove electron is the same for a medioscopic particle. When we go to a molecule, the main difference is that needs to be incorporated in electronic structure is the nuclear coordinate are changing as you add and remove electrons. So here is an example. This is not ferrocene, but you add another group on top and iron in between. For illustration purposes, ferrocene was not put here, but if you add an electron, there's reorganization. If you remove an electron, there's reorganization. So this shifts these two curves off from one another. And instead of treating the nuclear coordinates classically, if you treat them fully quantum mechanically, and you get their corresponding nuclear wave functions for simplified parabolic Hamiltonian, what you arrive at are specific allowed transition energies for adding and removing electrons. They're separated by the frequency of this oscillation mode. Okay, so these are called, the rates that determine this are called Frank-Condon overlap factors. And so if we take this picture, this fully quantum picture of nuclear transitions, what we end up with are these two distributions here, where the height of the distribution, we call this arbitrary dose. This is really a Frank-Condon overlap factor intensity between these wave functions and these wave functions, or vice versa, when you're going up and down. And you see they look very, very similar to the Grischer distributions we start at, but these are fully quantum. There's no electron transfer in these gaps here between these lines. It's prevented by the Frank-Condon principle. And what's interesting, though we won't go through it in this talk, is if you go to much higher temperatures, this only appears, say, at 4 Kelvin, liquid helium. go to very high temperatures, these distributions broaden out, they come closer together as you treat the mode more classically, and you get the Grischer-Hopfield distributions, the same picture that we started with before. So we investigated this type of system in collaboration with the Grutter group at McGill, who did all these measurements. I was very lucky to collaborate with them on the theory part. We met in the hallway and asked me, Kirk, can you take a look at this? And I was really proud to be part of this work. So this was the first observation of quantized electron transfer, as far as we know, at an interface. So what they did is they brought an AFM tip in. It's biased with a voltage. So a fraction of the voltage will drop between a ferrocene and across a tunneling layer. And then as you shake the tip up, or you oscillate the tip up and down, it's harmonic oscillation. You change the voltage very slightly that's acting on this molecule here, and so that will very slightly remove and add electrons from that molecule here. And here's a typical image of, it's a force interaction measured by the Coulomb field. So it's much larger range than looking at a single atom, because you're looking at the Coulomb field created by the entire system of the electrons added or removed. Okay, so they did this experiment, which you might want to call vacuum electrochemistry. You can't do this at room temperature because you have to go to very low temperatures to see this quantization effect. So you need to do it in a vacuum or something that's frozen. And so they brought this AFM tip in, they biased this ferrocene. And if we take this same total energy to electronic structure energy here, you have discrete quantized levels where you can place an electron, and then levels where you can remove electrons. But instead of being a continuous distribution, they're discrete. And so this, I don't have the movie with me here, but if you go to the paper, there's a nice supplemental movie that animates this a little bit better. But what you can think is that when you're on resonant, you're adding and removing electrons equally. So you let a few on, you let a few off, you let a few on, you let a few off. You're standing over the molecule for a while, so you get an average measurement. And then you move your bias a little bit off, and here, because your voltage is not high enough, you're only able to kick a few off or kick a few on, and vice versa here, because here you have symmetry, and you can add an equal number and remove an equal number. Here you have a preference for removal versus adding, and the charge balance dictates that the two must be equal. Okay, and so this transfers into these rate curves here. If you integrate these two curves here for sweeping the voltage past. And the important point is you get these discrete plateaus, and this comes from the quantization, the nuclear quantization. And in their AFM measurement, their force response measurement, they see exactly this quantization features, these shoulder features here in the force measurement from this molecule. And so this is fully quantized electron addition or removal, or fully quantized electrochemistry, if you like it, where both the electrons are quantized and a nuclei quantized. Now, from a theory perspective, why this is so interesting is that if you go back to the original literature on electron transfer theory, going back to Marcus and others later, the 50s, 60s, 70s, 80s, they all start from the fundamental fully quantum Hamiltonian. And then they say, and we approximate that we can treat the nuclei classically, and then you get to Marcus theory. But they say, in principle, you should have fully quantum effects also in the nuclei. And that's exactly what's seen here, exactly a textbook theoretical prediction. So we were able to get good agreement between theory and experiment. This is a nice, it's always very nice to get experiment and theory where they agree without incorporating a lot of fudge factors. So this is something we're both quite proud of. Okay, so the punchline from this talk, I realize it was a lot of technical details, but the punchline from this talk is that we can use electronic structure theory, the same type of theory you would have used to describe a diode or a transistor, but bringing in concepts such as a Stokes shift or reorganization, Grischer-Hopfield distributions to understand, for example, voltammetric curves that look like this, or multiple electron transfer voltammetric curves that look like this here. So there's a wide range of electrochemical processes that you can understand using this electronic structure picture. Now, I have not said you can describe all electrochemical processes using this picture, because the real frontier, the real difficulty is in understanding more complex chem-absorbing reactions or multiple reaction step reactions, where you have absorption of a species and then it goes one step and then a next step and the next step, for example, 4-hole transfer or so on, and water splitting. These are much more difficult. But the motivation here is that we can use this electrochemical picture to also help drive understanding of other interfacial non-equilibrium electron transfer electrochemical phenomena, and bring these two together and hopefully have more success. And I think there's a lot of interesting work going on around different communities that are doing this. This is a work from a few years ago or so, more from the Crumlin group, where they did just this at LBL in California. They used the ambient X-ray photon spectroscopy. They kicked electrons off as a function of bias, and they can see these very same point of zero charge effects in an electric double layer in terms of the shifting of XPS peaks for a given measured XPS peak, like, for example, from sodium 1s. So I won't get into details of this paper. This is not my work, but I thought it was a really nice paper that further brings the experiment of connecting electronic structure ideas, which are these XPS peaks, to electrochemistry. Okay, and then of course there are the applications that motivate everything, because eventually we want our work to be useful to the broader community, to new energy storage or renewable fuels or advanced manufacturing or new ideas of computing. There's lots of ideas out there, and it's all worthwhile to one way or another worth pursuing, and we can always gain from an improved understanding to help further these systems. Okay, I'd like to thank the graduate students that have participated over the years in this work in various aspects of it, and also for the collaborators at Alton McGill, Peter Gruder, I mentioned, Chris Howard at University College London on the pseudocapacitive, and also Professor Mallinareedharan at IIT in India for the collaborative work on the blockade effects. Okay, so hopefully I haven't gone too fast or too slow, but there we go.
Right. Thanks for this nice talk. I had a question about the theory you presented at the beginning for the effect of the solvents on the energy.
Okay.
Is this treatment fully adiabatic? And
okay, yeah, so that's a very detailed question. So there's adiabatic and non-adiabatic. So this is in the spirit of Marcus theory, where it's a tunneling reaction. But yes, you have systems that are at the transition between adiabatic and non-adiabatic. It's not clear, and this is one of the main challenges in how you apply electronic structure theory. And there's a lot of leading contributors which are working on this now. The transition between adiabicity and non-adiabicity is still really fundamental in various fields of chemistry, not just electrochemistry. And I would say that it's still, a developing front how to properly treat. And I'm not going to take a stance either way, that it depends on a particular system, whether you can justify an adiabatic or non-adiabatic or some mixture in between where it's at the transition. I'll just leave it there.
small system, like it's not a particles where it shows like state, but in the case of a liquid, where you have a lot of informal erosional relaxation. I mean, water, you have also hydrogen bonds that you may need some additional correction.
You could use additional correction. So the question is you could always use more corrections. Like you always have a more accurate Hamiltonian. So the question is, what are you correcting, right? So, the eigenenergies or the total energies could use corrections. And then the other side, which you mentioned, is the correction on how you treat, how the electron actually propagates, either doing it adiabatically or non-adiabatically. So again, I would say it depends on the problem. And, for example, we're in the process of doing a study on the solvation actually of Fe2 plus Fe3 plus, because it's a canonical system. And it turns out just calculating these electronic structure energies from first principle is very tricky, because you want to get agreement between both the single particle and the total energy picture. And this is a non-trivial thing. You have to have a functional which can provide that, can provide linearity with respect to the number of charges you add. So the long and the short of it is, yes, corrections can always help, but it has to be justified in the context of what that Hamiltonian is actually trying to say. What is it addressing, right? Not just throwing a machine at it and saying, oh, I did this functional I did this electronic structure calculation, therefore it's correct. What is it actually correcting? So that would be my opinion.
Can you tell us more about the interface phenomena? Because you mentioned there is an absorption there.
Yeah.
So kind of building effect.
Pardon, I didn't hear you. Yeah. Yeah, you have a double layer, Helmholtz layer, inner sphere, outer sphere. So this is very complicated. In this picture that I've shown here, it's a phenomenological description to describe the IV curves. But of course, this is something that we're looking at investigating in more depth, but this is a very complicated problem because you have many atoms, you have a huge number of statistics. And so one of the questions would be, that is perfectly valid, is it that I have for myself, is that in this phenomenological description, is it a simple capacitor effect that drives this reaction, or is somehow there a dance between one ion that's kind of acting more as a shielding, screening that's inside one of these layers, and is somehow kinetically bouncing into, like, how is this actually happening? Is it really a simple capacitive argument, but are there subtle interactions at the atomic scale that are assisting or driving or pairing to drive these events? So again, I think one of the reasons that this has not, there are groups that are tackling this from various localities around the world, but one of the reasons that until the past 10 or 20 years it hasn't been tackled is because the statistics is so vast. You have a lot of atoms, you have long time scales, and so you have to explore, and you have complexities, atomicity, non-atomicity. So you have to explore, a large space of atomic interactions to winnow down and get closer to answering it. But at the same time, it's very interesting because it's not a fully addressed question. So I'm not trying to say that this is the end of the story, by no means, but it's like when you describe a transistor, or let's say let's call it a strongly correlated transistor, you can draw a band diagram, you can get a pretty good idea of what's happening. But there's subtle electron-electron interactions. There might be some defects that are diffusing during the gating process. There might be some subtle things that are actually heavily influencing what's being measured, right? So the same thing here. We didn't treat all those aspects, and there could be some very important subtleties. But in order to address that, in order to move the model forward and move the field forward, there needs to be this, okay, a crumb measurement like at LBL, and then a theory modeling. And then sometimes the model will be wrong, sometimes it will be correct. And then, so we have this interplay. So I think that's my, I never have 100% confidence in a model because there can always be a missing term, right? But I feel that this is a very interesting intersection of ideas.
So I have a question about the potential drop. Can you go back to that slide? So I see downward and upward pendulum.
Yeah. Let me.
Yeah, maybe this one is fine.
Yeah.
Yeah. So can you calculate the barrier height? Barrier height or width?
This barrier height here? Yeah, in principle, you can calculate it. How accurate it will be, that depends on your electronic structure method. That gets back to your Hamiltonian, right? So you need to know, what are the energy levels that you're tunneling through? What's the distance from this energy to those energies? Are there intermediate states that may participate in that tunneling process?
And can you correlate with the redox potential of the? This barrier height, is there anything to do with the redox?
Yeah, so this tunneling barrier height will affect this, and this is the first order treatment. This is from the Grecian. This is not, this is not something my team developed or I developed. This is from Grecian and Hotfield, but it's this tunneling term here, this quantum mechanical tunnel. So this is like a simple e to the minus barrier height, etc. Simple tunneling expression here.
Okay. Yeah. And it has nothing to do with the metal work function, right? So it works for any metal, any work function.
Well, it would be affected by the work function because that will affect the alignment with a given liquid. So, I wouldn't say it's not affected by the metal work function, but it is something that can be calculated in principle. It's just a difficulty of calculating it in 100% accuracy, or the number of atoms and statistics of the process that's happening and the defects that are possibly participating in that transfer process. For example, there's a lot of nice work from UIUC where they talk about hydrogen-coupled electron transfer. So there you have a hydrogen ion. Can it somehow assist the process or couple to the process? There's lots of things to consider.
Right. Can I ask one question, please? So I guess just you have to wait.
I'm going to.
So just to get more of an understanding of what methods you're using to get these distributions, you kind of glazed over that really quickly, where it seems like you only have one complex, like an isolated complex vacuum, and you're studying the energy to put an electron on or take an electron off of that, and you're able to get these sorts of distributions. Is that really what you're doing?
Yeah, so this particular model is just purely analytical, right? But if you want to get this in a simulation, what you have to do is put an ion in a box, a simulation box, if you like, or in a agglomerate box, a water box, and then you have to add or remove the electron and calculate total energy that changes when you add or remove the electron, and then also calculate the eigenstates that occur and make sure that those two quantities agree.
Okay. Because it's surprising that you can get away with only one ion and you don't have to consider somehow the energy, just the electron hopping from one ion.
Yeah, I mean, at higher concentrations, that will become an issue. Yeah.
Saturated near the surface of your cell, basically, near the interface of your cell, that electron transfer, because it's,
Yeah, you're right. I mean, it can get a lot more complicated.
have an electron on them? Like when you see that black.
No, that means that very few of the ions have an electron on, but the ones that you're tunneling into, you fully saturated. You can't add any more.
Near the interface.
Yeah.
Concentration.
Yes. So if we go back here, the current is actually, so this is a surface concentration term.
Okay.
So the total current is the rate to each ion, which is a function of the bias, and then the number that you can tunnel in, the surface concentration you can tunnel into times the charge. This will give you coulombs per centimeter squared, for example, or amperes per centimeter squared.
Yeah, so I'm just trying to picture a little
Yeah.
bit more.
So when you transfer,
Electrochemical cells.
yeah, this is a phenomenological description of what's happening, and obviously there are lots of subtle atomic effects. But I think the long and the short answer is that the tools to describe all of these atomic effects or electronic effects, which are adiabaticity, non-adiabaticity, these are still being developed and integrated. It's
it's very ideal system that you're studying right now, metal versus the liquid. And I was wondering if you, in your statistical model, if you are considering the randomness of the liquid part, because I would imagine the metal is very crystalline, the metal part, and it's obviously it's solid, but the liquid is constantly moving and it's random.
Mhm.
So do you usually consider that into your analysis? And
Yeah.
why I'm asking this is, what if you want to see the interface between gas and the metal? That would be the one thing that would be very different between the liquid and the gas.
Mm-hmm. So the randomness in this particular model is taken through the statistics, the of the Boltzmann distribution applied. Okay, so that's the randomness of the nuclear coordinates is taken through this Boltzmann distribution. Now, there have been lots of papers, and we've done this work as well. You can run an atomistic simulation, and you'll get these same, basically you get these same distributions by sampling and averaging over time. Yeah, for different liquids. I mean, we've primarily concentrated on water, but this is a kind of a generic picture that works for most liquids. The subtlety comes in of quantities like the pair correlation function. What exactly are these energies? You see here, I didn't write any values, right? So in order to know these energies, you need a proper Hamiltonian. And this is not necessarily parabolic. It's definitely not parabolic. It will have some slight deviation from parabolicity. So these are assumptions, in the model. But phenomenologically, it captures these types of reactions fairly well. But obviously, there's a lot of fun and interesting work to be done to refine these models, to get closer to experiments, to get closer to spectroscopic information.
On myself.
Yes.
It's about the quantum capacitance that you talked very shortly about. I was wondering, how is this molecule basically behaving? Is it more like a metal or plasma? Maybe we could even say that you have so many states possible that it's becoming a continuum, and that the cartoon picture would be basically it would be basically a plateau without it.
Yeah. So this is you're. By the way, we don't call this quantum capacitance because I'm from a solid state physics background. That means something. We call it in this field. When they first started, they call it quantized capacitance. So we just stuck with to avoid adding more terms and more confusion. We just stuck with their word. This is from Murray's group and others. I think they coined this term in North Carolina. But anyhow, yeah, the idea is that these peaks are separated by the Coulomb U. And so, yeah, if you make these disks big enough, it functions just like a metal. Like an infinite becomes like graphene, and you're basically intercalating graphene. But what we're arguing is there's this limit where for storing the same number of electrons per unit area, let's say, 1 electron for every 6 atoms. Okay, if you try to store 1 electron for every 6 atoms, but you shrink the size of the disk, it pushes up the voltage that you want to store them, because now they start to Coulomb interact through the U. Okay, and if you don't make the disk too small, they don't push on each other too much, that they're so-called redox peaks or Coulomb peaks, where they add them, overlap in a very smooth way to give you sort of a metallic response, but through a Faradaic mechanism. Yeah.
Any last questions? If not, let's thank Kirk one more time.
Thank you.